Okay, so it is in fact unfortunate that we had only 2 classes for GR, but hopefully we covered the main ideas of GR. Of course, we couldn't cover everything from a general relativity course normally, but at least we covered some things that we need for cosmology, and of course for further topics that we will cover in the main school. So, since we're starting cosmology, the first question we need to ask ourselves is what is cosmology? Okay, and this is something, a basic question that I ask at the beginning of my lectures when I take the course cosmology at BRAC. So, what is cosmology? So, of course, if you want to break it down, cosmos and logy, it means the study of the universe or the study of the cosmos, right? So, how do we study the universe? What is the exact technique to study the universe? এখানে একটা complication আসে because universe, we don't really understand it very well, right? From our viewpoint where we are at Earth, it's very insignificant of us to actually look up at the sky and devise a particular theory to explain what there is out there because we're so little, right? However, physicists and also philosophers, I would give it to them as well, have been thinking about cosmology for a long time. And this is something that I also quote in my class, that cosmology is a new science, but cosmological questions are as old as mankind. Which means that when we did not have the science to build such topics and theories, we still thought about the universe, right? We still questioned where we came from, how did all of this come from, where did we start, where are we going to end, and so on. So therefore, cosmological questions are as old as mankind. And these are the very questions that we try to answer when we study cosmology. So there are two particular aspects to approaching building a theory like this. একটা হচ্ছে we try to build something from small to big, meaning we can devise some theories at Earth. For example, when Newton discovered gravity, right? We have this very famous story that an apple fell on his head and all of that stuff. So the falling apple idea was later on devised to make models of elliptical curves around the sun, and how planets orbit the sun and so on. So we took something small, some model experiment on Earth, and we try to take it to bigger scales. So that is one approach to cosmology that we do. We try to test a theory at Earth, and then we try to devise some sort of assumption about it at grand scales. Another approach is that we make theories of the universe. We make certain assumptions and theories, and we try to see if they work out experimentally, like we did for black holes, right? Black holes have theoretical frameworks that we try to test experimentally by making acoustic black holes in labs and so on. So these are two particular approaches that we can take to study the universe. Now, normally I prefer the theoretical approach more because I'm a theoretical physicist. So that is why we're going to go on from there. Okay. So to understand cosmology, we need to understand the universe, like I said. And particularly from the facts that we know today, the universe is segmented in particular phases. So let me jot down some of the history of the universe that we know. So if I want to look at how things started, let me try to make a graph for better understanding. So let's say the universe started from here. Okay, and there is a particular reason why I'm starting right at the middle of the graph, but we will understand that later. So let's say the universe started over here, and from experimental data and observations, we know that the universe is expanding, right? So therefore, the universe expands, 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 and now we are somewhere over here. So we are here today. So if the universe started from here, this is quote unquote when Big Bang happened, right? At least that is what we understand from our general understanding of the universe. And this is typically when the universe evolved. So this is some time scale. And the universe expanded, 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 and now we are somewhere over here. Okay? So this particular part in the evolution of the universe can be segmented into particularly two phases. One is called the radiation domination era, and the other is called the matter domination era. Okay? And the reason why this expansion, this curve that I'm drawing over here, is not really linear is because the universe evolved differently in different phases of these two. So this is more or less the picture that we know and we are sure of. But over here, particularly this area, we see that, it's a little different, right? In the sense that what is exactly happening? We have the expansion, so it's moving up, but then we see that this is curving downwards slightly. So we are at an era where the evolution of the universe is not really being treated the same way as it did in the previous eras, right? So this particular era is actually called the cosmological constant era, or you can say the vacuum energy era. Now, why is this different? Is because throughout this whole time, we have the universe expanding. That's all good. But here we do have the universe expanding, but the expansion itself is increasing. So the rate of expansion is, positive. So that means that the expansion is not only, moving, but it's moving at an accelerated rate. So that is what's different. So this is how we can segment the universe into the phases that we know is happening or has happened in the previous time slice. However, we now need to question what happens here, right? Because in cosmology, again, we try to study the universe. And one fundamental question of studying the universe is, how did it start? Where did it come from? And we can only answer that question if we know what laid conditions to this particular point in time where the Big Bang, or the so-called Big Bang, happened, or the universe started, right? So now we need to understand the physics of this particular era, which led to the conditions over here. And that is essentially what we do in cosmology. Okay, we try to build a model of an early universe that gave or laid down conditions that started this particular point in time, and then how these conditions led to the evolution of the universe that we see today. Okay, so let's start by building this theory. And when I take cosmology at BRAC, what I normally do is try to justify why we need GR to essentially build this theory. But since we've done GR, I'm going to skip that, and I'm going to just move on to the idea of the universe that we already have, which is the fact that the universe is expanding. So let's look at the model of the expanding universe. Okay. So, like I said, we do have good evidence to see that the universe is indeed expanding. And the way we incorporate that expansion is by reparameterizing our coordinate system. What we do is we sort of take a different frame of coordinate systems. We call them the co-moving coordinate system, because we want that particular coordinate system to move with the expansion of the universe. And why we do that is just to simplify our calculations. So if you want to take a look at how these coordinate systems work, take a grid. And the way you would measure distances in this grid, let's say if this is point A and this is point B, to go from point A to point B would give you a certain distance from point A to point B, right? Now, if we incorporate this in an expanding framework, let's say now the grid has expanded. So the same points A and B would be in the intersection of the grid lines, right? However, the distance is not the same from A to B. Now, this particular distance is called the physical distance in cosmological terms. And therefore, you can see directly that the physical distance is not going to be the same from A to B as the grid expands, right? However, if you reparameterize your scales or the distances just to incorporate that some distance exists from A to B, which is in the intersection of the grid lines, you can say technically that A and B would be in the same distance because they still lie on the intersection of the two grids. Right? Does that make sense? So this is how we incorporate the co-moving system, where we say that the coordinates in the co-moving system are expanding with space. Therefore, we do not feel the expansion. It's like moving inside a car, right? If you're moving inside the car, you don't feel the speed of the car itself. The car is moving, let's say at constant velocity, you're inside the car. If you're moving along with the car, you will feel like you are sitting stationary, right? So it's something like that. You use the coordinate system to be moving with the expansion of space, so that in that particular coordinate system, you don't feel the expansion, which makes our calculations very simple. Okay, so in addition to this particular coordinate system, we define something else in cosmology, which is called the scale factor, which is denoted by A. And the scale factor is essentially what measures the expansion of space. Okay, so essentially we set A, let me write it here. We set A, denoted with a subscript 0, as 1 today. So this subscript 0 stands for any calculation or any measurements that you take today. I know this is a very weird notation. Normally we set A naught to be something that has an initial value, but A naught in cosmology or any object with a subscript 0 is essentially measurements taken today at the present. So A naught is said to be 1 today, and we will see why we can actually do this parameterization later. So particularly scale factors, or this particular scale factor, measures the expansion of space, and it can range from 0 to 1, where we set 1 to be the scale factor today, and previously, because of course, since the universe is expanding, universe's size, ekhon jototuku, it was definitely smaller before, right? So therefore, the scale factor was smaller than 1 in the previous time, which means that the expansion was smaller. So therefore, it is smaller when we go back in time, and it starts from 0, because of course we don't want the scale factor to be negative, because we know that the universe is expanding, not contracting. So the scale factor that measures an expansion should be positive. So that is the particular scale of the scale factor. Now, in addition to the scale factor, what we also need to understand when we're studying the universe is how this particular scale factor evolves, right? যেহেতু আমরা একটা expanding space নিয়ে কথা বলতেছি, our universe is expanding, we need to see how this expansion actually evolves, because we need a good picture of what happens over here over this whole time, right? So since expansion is taking place over this whole time, we need to see how this particular expansion evolves, and the way we do that is by finding the evolution of the scale factor. And in addition to that, one other thing is also important to study about the universe, that is how the universe's geometry works, right? And as we've seen in GR, we see that components or constituents in the universe actually play a role in the curvature of space, right? So therefore, how the universe is shaped, or the geometry of the universe, is also important to know how the scale factor evolves, how the components of the universe evolves, and so on. So we also need to understand the geometry of the universe. And that is beautiful because we have a theory that actually relates the two. We can relate the universe components, constituents, with the geometry of the universe, and that is through the beautiful equation of Einstein's field equations that we've seen in our last class. So essentially, that is why we use GR as our fundamental framework to explain the universe. So since we are talking about geometry, we need to talk about particular possibilities of the shape that our universe can take. Now, there are 3 possibilities. And 3 possibilities are, if I'm talking in curvature terms, can be curvature 0, positive, or negative, right? So when we have curvature to be 0, we call it to be flat, right? When we have positive curvature, we call it to be closed. And when we have negative curvature, we call it to be open. Okay, so these are the 3 possible shapes or geometry that our universe can take. Now, if I want to, explain this further, a flat universe would be Euclidean, which means it would abide by a particular geometry in E3. And why I'm calling this E3 is because, we have 3 spatial dimensions, right? So the space, which is flat, would be 3-dimensional. And what I mean by Euclidean is that in a Euclidean geometry, when you have parallel lines, they stay parallel as long as they're not deviated by anything else. So if they're free to move, these parallel curves will always stay parallel in flat space in Euclidean geometry. Now, the other possibility is that the universe is closed, which means, or you can relate this analogy of a closed universe to say that these particular parallel lines converge. Okay, and this is very close to S3, which is a spherical geometry, and it has positive curvature. Now, similarly, when the universe is open, you can think of this in the analogy of the parallel lines again to diverge. And this is similar to H3, which is a hyperboloid geometry. And you can think of this as, if you want to visualize this, if you have a saddle and you have two marbles on the saddle, it falls off, right? The saddle. So the parallel lines in that sense of the trajectory of those marbles diverge. So in that case, this is an open universe, geometrically. Okay, so like I said, for us to understand the universe now, we sort of figure out যে আমাদের হচ্ছে ঠিক আছে possibility থাকতে পারে তিন রকমের geometric এরকম এরকম হইতে পারে, but then we also need to understand, like I said, the evolution of the scale factor to understand how the expansion evolves. So in that case, we need a certain relationship of the scale factor with time. And indeed, we know that the scale factor is supposed to be a function of time because the scale factor changes as the universe expands, right? So in that case, we denote the relationships of the scale factor with time, t, and this t is essentially the physical time. And the reason why I'm writing physical time, because you understand that the notion of physical time and co-moving time is a little complicated in cosmology, right? Physical time is something that is, set. This is the time from, this is the time you can measure, right? However, cosmic time or co-moving time, in other sense, can be different if you parameterize our co-moving system in a particular way. So I write physical time when I mean time that you can actually measure. So if I want to write the relationships of the scale factor with time, you can understand that, of course, it will vary differently for different phases of the universe, right? When we are having the radiation era, time and the space will scale differently, and therefore the relationship with time and the scale factor will scale differently as we are in this particular phase of the universe, right? Even in matter, you can see that the evolution will be different. The question is why that is so, right? Maybe you can ask me this question, Jay. Why is the universe evolving differently at different phases? Like I said, curvature is related to the components of the universe, right? So here in radiation era, when I say radiation dominated era, what I mean is that the universe was composed heavily and dominated by relativistic particles. And relativistic particles are different from non-relativistic particles in the way in their dynamics, right? So of course, if the universe is dominated by different types of particles, that means that it will shape the universe in a different way, right? And if the universe is shaped differently, of course, the universe will evolve differently. And therefore, the scaling with time is going to be different in relation to what the universe holds at that particular time. So in that case, that is why it scales differently. And we have different scales for our radiation domination, matter domination, and particularly also now in the vacuum energy or the cosmological constant era. So let me just jot them down. I know I don't have the time to derive all of them, but we have to take it as is. So we will see that during radiation domination, we have the scale factors to scale as proportional to t to the power half. And during matter domination era, we have the scale factor to scale with time as t to the power of 2 by 3. Okay. Sorry. I'm just very scared for this to spill. So now that we've understood that we have the relationships of A with time, the most fundamental object now to define is the metric, because like I said, geometry is also important for us to know, to understand how the universe is, right? So therefore we need to define the metric of the universe. So without Jamal, let me just go through some trial and error. Let's see what we can do about it. We understand that there could be three possibilities across a flat, open, closed, but we need to devise these particular possibilities into the metric, because the metric is what defines the geometry. So in that case, let me just start with a generic metric. And as we've seen in our GR classes, I can write the line element. I can write the line element with the metric. And as you've seen, I wrote it as the following. So this is a particular space-time metric, very general. I haven't defined the, this is a space-time line element, but I have not defined the metric yet. Okay, so in SR, normally we use the Minkowski metric, because when we are doing special relativity, we know that, the underlying space-time is flat. However, in GR, we work with non-trivial spaces, as we've discussed before, right? So in this case, I cannot really, devise a particular metric just as is, because I don't know how the universe is curved. So in that sense, I need to understand, or at least observationally understand, how the universe is, right? So আমরা যেটা normally করি when we're trying to devise the metric of the universe is we try to see that how observationally the universe looks. And আমাদের এখন the only way we can test that is through looking at the CMB. Okay, and the CMB is basically this cosmic microwave background, and it is the farthest we can see into the past of the universe. And when we look at the CMB, we see that the CMB is homogeneous and isotropic. What homogeneous and isotropic means is that when you have homogeneity, it means that it is translationally invariant. That means if you are in the universe and you move translationally in space, you still see the CMB to be coherent, the same. So that means the universe must be translationally invariant. And what it means to be isotropic is that it's rotationally invariant. So if you look at different directions at the universe, the CMB still looks the same. That means the universe must be the same at all directions. So these are very significant symmetries of the universe. And of course, if I have these observationally there, I have to use these particular symmetries to define my metric, and that is what I do. And the way I do this mathematically is I try to sort of segment space into hypersurfaces that are called Cauchy hypersurfaces. And perhaps you don't have to understand this very well, but this is just like segmenting space into slices. For example, if I have this room, and if I slice each part of the room, let's say vertically like this, I will have multiple slices of the room, right? And if I bring them together, all of the slices together will give me what the room looks like, essentially, right? So I do that. I do the same thing to the universe. I slice it in terms of space slices so that I can sort of denote the curvature in each space and then move through space slices to determine, let's say, dynamics or trajectories. So if you want to look at this visually, let's say I have a space slice like this. So let me try to draw this in a better way so it's easier to understand. Okay, so let's consider that this is the whole universe. Okay, three-dimensional level. And what I'm trying to do is I'm trying to slice this box into small hypersurfaces. And if I take one of the hypersurface, let's zoom in on one of the hypersurfaces, then I will have something like this. And this is, remember, very thin. So we know how space-time works, right? In SR, we've seen that if we want to draw a light cone, let's say something like this, It's not very nice. But we understand that time moves upward and space moves sideways, right? So that means that if I'm moving on this hypersurface from this point to this point, I'm only moving in space, right? So that means that these are space-like slices, which means all over this slice, time is constant. And if I lay another slice on top of it, this will give you a notion of different time, right? So that means this, let's say, exists as time t equals to 0. This upper slice will be at some, let's say, t equals to 1. So if you move from the initial slice, the upper slice, that means you're moving in time. Okay. So in this way, you can sort of, model trajectories in the sense that if you move in space and time, you would be moving through the slices. And depending on which point in space you're moving, you can always characterize it in particular points in the hypersurfaces, right? So this is how we model the universe. And of course, there are more intricacies to this, but just visually understanding, this is what we can do. Now, in terms of geometry, when we consider geometry of the universe, we consider that if the universe is, let's say, flat, it means that all these hypersurfaces are flat intrinsically. Okay, so you have all flat universes, all flat hypersurfaces stacked on top of each other like this. And the reason why this is called a Cauchy hypersurface is because if you have an initial point on hypersurface, you can essentially, make this into an initial value problem, a Cauchy problem, and you solve it for later evolution. Okay, you can evolve it in time. So let's say if my universe is flat, I can have all flat hypersurface stacked upon each other. If the universe is spherical, let's say positive curvature, I can have, positively curved hypersurfaces stacked upon each other like this, and so on. And if it's the other one, which is negative curvature, I can have them stacked on top. Okay, I'm not really good at drawing this, but you understand the picture, right? So intrinsically, all the hypersurfaces have the same geometry. Now, what I need to do now is essentially আমরা তো টাইমকে হচ্ছে constant রাখছি. So what it does for us, it makes our lives easier in the sense that we can essentially just figure out the metric of the spatial hypersurface and then maybe add time later on. But আগে হচ্ছে geometryটা যেহেতু space-এ encoded, maybe make a spatial metric first and then encode time with it because time is not being affected on the spatial hypersurfaces, right? So we can convert our 4-dimensional metric to a 3-dimensional one and just do it for space. So in this sense, if I have a flat universe, then I can write the line element for a Euclidean geometry for a flat space, and it will look something like this. Okay, and remember what DL is essentially the 4-dimensional line element. Oops. 4-dimensional line element and its spatial part. Now, this 4-dimensional line element is the line element of the universe. We add the scale factor over here because we want to denote an expanding universe. And expanding universe term scale factor is added to the spatial part of the line element, which is denoted by dl squared. And a dl squared আমি হচ্ছে figure out করতে চাচ্ছি for the particular space-like hypersurfaces. Okay, so now if I have, let's say, spherical space or closed universe জন্য যেটা okay ঠিক আছে. So let's say I have it for spherical space. In that case, I can encode my dl squared, which is the space-like metric, as to be of a geometry of a 3-sphere. So I can write it as where this abides by the equation of a sphere. And R0 is essentially the radius of the sphere. Okay. Similarly, I can do it for hyperbolic space. And I will have a similar equation, except now I will replace the plus with the minus because it abides by the hyperbolic equations that is like this. Okay. Now, moving on, what I want to do is I want to incorporate this whole thing into one metric, one particular line element that should explain everything in the universe that we know, at least theoretically, right? So I can do a bunch of things, and maybe I will not show the derivation completely, but what I can have at the end is by just, using all of these equations together, and that one, of course, is I can write the line element as the following, where I'm considering K to be 0 when I have flat space, Euclidean geometry, 1 when I have closed geometry or basically spherical geometry, and -1 when I have hyperbolic. So I can incorporate all of that into one spatial metric. I keep saying metric, but spatial line element. Now I can also incorporate this in polar coordinates, where I can write dl squared as dr squared by 1 minus kr squared by r naught squared plus r squared d omega squared, and d omega basically has all the thetas and phis in polar coordinates. Sorry, this is spherical coordinates, polar spherical coordinates. Okay, so now আমি মোটামুটি শেষ করছি spatial পার্টটা. Now I have to incorporate the space and the time into one line element, which is 4-dimensional, right? Incorporating space and time both. That is the metric that describes the universe, and it is called the FLRW metric. So it's named after 4 people: Friedman, Lemath, Robertson, Walker metric. Now, in some textbooks, you might find FRW or even Robertson-Walker metric, but I like to give credit to all 4. Okay, so I normally call it FLRW. So this FLRW metric in polar coordinates look like the following, where you incorporate dl squared over here. So you incorporate this term in the spatial part over here, and you can write this as dr squared 1 minus kr squared by r naught squared plus r squared d omega squared. Okay, so this is essentially the FLRW metric that not only describes the universe, but it also incorporates the symmetries of the universe, specifically homogeneity and isotropy. Now, an important feature of this metric is that it has a rescaling symmetry. And what this rescaling symmetry is essentially is that if you take and scale the scale factor by some factor lambda, and also scale r, which is the r from here, by some factor lambda, and also r naught by some factor lambda, simultaneously, it should keep the line element invariant. And this is exactly why you can scale the scale factor to be 1 today. Okay, you can take the scale factor 1 today because of this particular rescaling symmetry. Okay, so this coordinate r over here, we're going to call it a co-moving coordinate, because we are going to assign a co-moving system with this. Remember what co-moving systems are? Essentially, co-moving systems are moving with the Hubble flow. And what I mean by Hubble flow is the expansion of the universe. So R is essentially moving with the expansion of the universe, and therefore I call this a co-moving coordinate. And to see this better, or to understand how co-moving coordinates and physical coordinates relate, let's look at an example. Let's take a particular galaxy. Okay, so let's say I have a galaxy over here. Okay, and I understand that r, if is the co-moving coordinate, it should move with the expansion of space, right? So in that sense, I could relate the co-moving coordinate with the physical coordinate by the scale factor. So in that sense, I can define r physical, which is the physical coordinate r, with the co-moving coordinate r by adding it or basically multiplying it here with r, which is the co-moving coordinate. Okay, so this is basically the relationship. Now let's get back to our example and let's look at this galaxy. And I want to sort of measure this galaxy's velocity. Okay, if I want to measure the physical velocity of this galaxy, which is denoted with v physical, it should be essentially a time derivative of r physical, right? So it should be dr physical by dt, right? And since we know r physical is given by this, where r over here is the co-moving coordinate, I can essentially find v physical by taking a temporal derivative over ar, right? And remember, the scale factor is also a function of time. So when I have a temporal derivative on a, this will treat it as a product, and therefore I will have to use the product rule. And what I will finally get, okay, let me just write this down so that you can see what is happening. This, right? So over here, I can write this as a dot, and r from here, I can write it as r physical by a. So this will basically give you something like this, right? Plus this dr by dt essentially should give you r dot, and this r dot is some co-moving derivative, temporal derivative, right? So therefore, I have some temporal derivative of a co-moving coordinate r. Now a dot by a, from here, I define this to be h, which is Hubble parameter, plus this term over here, I name it as v peculiar, which is the peculiar velocity of the galaxy. Now let's try to understand what this gives me. So when I actually figure out the physical velocity of a galaxy, এটার মানে কি? এটার মানে হচ্ছে আমি physical velocity টা দেখতেছি। তার মানে গ্যালাক্সিটা আদৌ কিভাবে মুভ করতেছে in all aspects of the meaning, whether it's moving with the expansion of the universe or it's moving on its own due to gravitational interactions or whatever, সেই পুরা জিনিসটা আমি সেই পুরা পিকচারটা আমি দেখতে পাচ্ছি, right, by physical velocity. And essentially that is what it tells me in the expression here, because this first expression over here should tell me how it's moving with the Hubble flow, because I have a temporal derivative of the scale factor a dot by a, which is given by h. So this should tell me how the galaxy is moving with the expansion of space. So let's say I have an expanding system. আমি যদি একটা stationary object to expanding system এর মধ্যে ঢুকাই, then that stationary object would move with the expanding system, right? It does not have its own velocity, but it would still move with the expansion. So this first term is what tells me that if I have that galaxy in an expanding universe, that galaxy would move with the expansion of space. What this second term does is, of course, the galaxy is not stagnant, right? The galaxy should have or could have a velocity of its own. Or if there is another galaxy, around or nearby, it could be pulled by the other galaxy and, could move towards it, right? So in a sense, the galaxy could have its own intrinsic velocity. And that is what is given by v peculiar, because as you can see from here, I have the scale factor multiplied with r dot, right? That means, remember, any co-moving coordinate when multiplied with the scale factor should give you something that is physical. So this is the physical velocity, or intrinsic velocity. Let's not call it physical, but this is the intrinsic velocity of the galaxy itself. So now physical velocity is captured by both of the movements, that the galaxy can also move with the expansion of space, and also it could have its own intrinsic velocity if it moves locally. Okay, so does that make sense? That is how you can sort of model the universe in terms of the Hubble flow, the intrinsic expansion of the universe, and intrinsic velocity of objects that are existing in the universe. Yes. No, it doesn't stretch out. Let's say, so, okay, this is maybe something that I can talk about later, but when we say expansion, it does not mean that local points get expanded. Okay, like for example, the Milky Way and the Andromeda, right? Or even let's for example consider us, the solar system, right? we don't get stretched out from the sun, right? It's not like the sun ek jagah ase and then we are here, but we get stretched out because of the expansion of the universe. We still know that the universe is expanding, but locally at lower redshifts, which I will perhaps explain later, but locally we don't feel the expansion as much because gravity takes over. Gravity is higher when we're closer. Okay, so gravitationally systems can be bound locally. So essentially, the galaxies don't get stretched. It's just you consider the galaxy to be a particle. Let's say, I know not a very good assumption, but let's say the galaxy is a particle, but that particle moves along with the expansion of space. You can think of it like that. Okay, but locally, nothing happens. In fact, when we have the Milky Way and the Andromeda, they are coming closer. That is what we know, right? Because of gravitational interactions. Because gravity takes over the expansion of space locally. Okay. So now we've defined age, which is an important factor when we're dealing with cosmology. And we can reparameterize our line elements in various ways. Maybe I'll skip that because it's not really important. But we can reparameterize our line element in terms of factors that make our metric simpler. Okay, because we see when we're dealing with the FLRW, this particular term or this factor over here could be complicated to deal with mathematically because it has a denominator that is complicated. Perhaps the denominator could go to 0 sometime. So to get rid of that, we can do many parameterizations of the line element, but because due to time limitations, I will skip that part. Now let's move on to the next important thing in cosmology. So I've more or less talked about geometry, and this particular line element depicts the geometry of the universe in terms of k, right? So if I have a flat universe, I can just put k equals to 0. This line element will tell me how a flat universe looks like. If I have spherical geometry, if I put k equals to 1, the same will happen, and so on. So geometry figure out করতে পারছি. Next কাজ যেটা সেটা হচ্ছে যে, again remember, I not only have geometry in the universe, I also have stuff, right? You have us, we have galaxies, we have large structures. So we need to understand the constituents of the universe. So remember that GR is the framework of building a model for the universe, and GR abides by the Einstein's field equations, and the Einstein's field equations are given by the following equation, right? So to understand the universe, we not only have to figure out this side, which depicts geometry, we also have to figure out the other side, which depicts the constituents, the components of the universe. So therefore, now we define the energy momentum tensor for the universe. So আমরা generically energy momentum tensor দেখছিলাম when we were doing GR. However, it's important to specify it for the universe. We need to understand what the universe holds, right? So a typical model is that we can decompose T mu into parts, and we can decompose, in fact, any tensor like this into 4 parts. So one is a 3 scalar, 3 vectors over here, and 3 tensors. And the way they can be related is by using the symmetries of the universe, right? So since the universe is symmetric, I understand that T00, which is the zeroth component of the T mu, we understand that this has to be independent of position. Why is that? Because of homogeneity, I know that it is invariant under spatial translations, right? So spatial translation and invariant মানে হচ্ছে আমি যে কোনো point in space নেই, it will still give me an invariant line element, right? So তার মানে it has to be independent of position, independent of spatial points. So therefore T00 যদি আমি compute করতে চাই, I know it has to be independent of points, space, and therefore I can write this as some temporal function, time function. And when I'm computing T0I, so let me write it the way I wrote it there. When I'm computing these two, they have to be 0. Why? In fact, what I mean by 0 is the mean of all 2 of these vectors should go to 0, because if I take 0j, let's say I'm only considering one direction, right? Just the jth degree of freedom. So in that sense, I know that I have isotropy in the universe, right? I have rotational symmetry, which means in any direction I look, it will still keep my line element invariant. Therefore, the mean direction, let's say I look this way, that way, and that way, if I take an average, they should go to 0, right? So therefore, both of them go to 0. Now, Tij form the কিরকম হবে? Now, this is a little more complicated to think about, but trust me on this. I don't have the time to really derive this, but trust me on this, that this should be proportional to some delta ij. Okay? And the proportionality comes from the idea that, well, around a point x equals to 0, you have isotropy. So that means at all directions, you have the same, you can see the same thing if you look in all directions. Now, this basically constrains your ij to be similar. Okay, so ij have to be equal, and therefore Tij has to be proportional to the Kronecker delta ij. And we know for a fact that Kronecker delta is also proportional to Gij, because somewhere in the GR class I wrote Gij was proportional. No, not in the GR class. In this class, I wrote this, remember? Over here. So, okay, to see this explicitly, maybe I can write this down. So remember, dx squared is given by g mu nu, dxi, so dx nu, right? So in this case, I can decompose this into temporal part and spatial parts, right? So over here, if I have this, when I have to have these to be symmetric. So in that case, I only write Gij to be dxi, dxj, where I and j are equal, right? Because I can only write it in terms of, let's say, dt squared, dr squared, d theta squared, and d phi squared. So that means I am doing the inner product between two same components. So I and j have to be equal in that case. And therefore, I have to have Gij to be proportional to the Kronecker delta I and j. And in that case, if I consider this, I can write this to be proportional to Gij. So that gives me a constraint on all of these terms. And now I can figure them out. And the C is over here to incorporate dimensionality. And these are 0. And Tij, I can write it as a component of Gij, but I need to have something in front, because proportionality fine, but it's not an equation, right? So to make this into an equation, I need to have something in front. And that something in front has to be independent of space, again, due to homogeneity. I cannot have position dependence, right? So I incorporate something which is also a temporal function. Okay. So I have my components, and now I can build my energy momentum tensor by raising one index. And the reason why I do this is to make it diagonalized. And I have the following diagonal matrix for the energy momentum tensor. Now, this energy momentum tensor is for a perfect fluid, and I'm modeling this perfect fluid to describe the universe. Okay, I haven't put anything else in the universe yet. It is just a perfect fluid, no galaxies, no human beings, nothing. Just a perfect fluid, which is, you can call it a 0th order universe. It does not have any sort of perturbations yet. Okay. So in this case, I can also write the energy momentum tensor in a covariant form. And I can write this as rho plus P by C. If my rhos and P's are confusing. So in a covariant form, I can write it in this fashion. And you will see, if we take a co-moving observer, where u mu's over here are essentially relative 4 velocities. This is something you probably have seen already in special relativity. So if we take it for a co-moving observer, this relative force velocity for a co-moving observer would look like the following. And you might question why it looks like this, because it's a co-moving observer, right? So co-moving observer maniki. Remember what co-moving means? It's moving along with the expansion of space, right? So that means that or intrinsic kono position change. It's just moving along with the expansion of space. So therefore, there is no deviation in the spatial parts. So these are zero. But of course, temporally we have C, because it's moving in time, of course. So therefore, a co-moving observer will have a force velocity which looks like this. And if you plug it in over here, you will find or recover the energy momentum tensor that I wrote. Okay. কোনটাতে? G mu. Oh, right. Yeah, sorry. Thank you. Yes, because I made a mistake because one of the indices have to contract, right? And that has to be lambda because I have uni over here. Okay, so like I was saying, that this particular force velocity, if you take it for a co-moving observer and you plug it in your covariant form of the energy momentum tensor, you should get this T mu nu back, because the T mu nu is for a perfect fluid, and the perfect fluid is indeed co-moving with the expansion of the universe. Okay. Now, next কাজ হচ্ছে আমাদের এই particular setup-এর evolution চিন্তা করা, right? Because like I said, cosmology ব্যাপারটা কি? The whole point is to understand how the universe is evolving, right? From an initial condition to now, how did it come by? So we need an evolution equation. And the evolution equation can be given by derivatives, right? And if you remember in GR, we do not only deal with a partial derivative when we're trying to find evolution, we transform it to a covariant derivative. So therefore, I need to find a covariant form or a covariant derivative form of the energy momentum tensor to see how it in fact evolves. So that is what I do. I want to evolve it, and for that, I look at the covariant derivative. And I compute the covariant derivative on T mu nu because I want to see if, this is conserved or not. And in fact, in GR, we've seen that this actually goes to zero. Right? When deriving the Einstein's field equation, it asserts the fact that the energy momentum tensor is covariantly conserved. So তার মানে হচ্ছে আমার যদি একটা evolution equation আসে, it should be through this conservation, the conservation of the energy momentum tensor. So in that case, let me expand the covariant derivative. And the way this looks is the following. And this should go to zero. Okay. Now, the next thing I have to do is just plug these things in, equate it to zero, and this should give me an equation. Specifically, should give me a continuity equation, right? So, therefore, let me write this down over here for reference. And we will try to manipulate this for our particular energy momentum tensor and our particular metric, which is the FLRW. Now, how would we essentially solve this? So we know the metric from the line element. FLRW আমি যে লিখলাম সেটা metric আমি define করছি. So I know what the metric looks like, right? So if I have the metric, I can figure out what the Christophels will be. Okay. And if I have the Christophels, I can plug them in over here. And I will have some sort of idea of the equation. Secondly, I also have my energy momentum tensor, right? Which I just defined. So therefore, if I put them down over here, I can then figure out an equation. It should give me an equation which, incorporates the metric of the universe and also the energy momentum tensor, and therefore should give me a total evolution equation of the universe. Okay. So now from here, I can figure out a sort of conservation by considering, let's first set nu equals to 0. Okay. Now, if I put nu equals to 0, let's see what happens. Now, I am sort of assuming that you guys know how to manipulate tensors. So I'm just going to go with it. And if I put nu equals to 0 over here, and the reason why I put nu equals to 0 over here is because this is the free index that I can fix, right? These are the dummy ones. So essentially, I cannot fix the dummy ones. The dummy ones will be summed over through Einstein summation. However, I can fix one, which is nu over here, and I can fix nu equals to 0 to get the energy evolution, because the 0th component of the energy momentum tensor is rho, right? Which is the energy density. So here, if I set nu equals to 0, my equation will look something like this. Okay. And if I assert 0 over here, mu has to be 0. Why is that? Because if mu is not 0, that means I would get a component in the energy momentum tensor which is off diagonal, right? But I see from here that the energy momentum tensor is diagonalized. So therefore, only diagonal entries are non-zero. So therefore, mu has to be the same as nu and has to be 0. So in that case, if mu is 0 over here, mu will also be 0 over here. And this is going to be my first term. Plus, I'm just going to write the others. And this is what I should get. এখন I'm going to plug in all the terms over here. So I know what T00 is. This is the 0th component of the energy momentum tensor, which is minus rho C. This I also know. This I don't know. So I'm just going to keep it as is. So what I will have eventually, by also asserting that D naught, which is the 0th derivative, is equal to this, I will finally have the following expression. Okay. Now, I haven't figured out the Christoffels yet, right? But trust me on this, Christoffel jodi ami bhagi, then I will see that two temporal indices at the bottom, which I mean by this, they all go to 0. Okay, particularly for the metric that we're working in. So if that is the case, then I can only have the Christoffels to be non-zero with lambda and mu to be spatial indices, number one. Number two, for particularly the FLRW metric, we will see that the Christoffel symbols vanish unless lambda and mu are spatial indices and they're the same, as in equal to each other. So in that case, we can only have a Christoffel that looks like this. And once you compute it using the metric, you will find this expression. So now we plug this in over here. So that means mu now only can be 0 or I. Okay, so for people who are confused and who probably don't know how to manipulate tensors, so these mu nus can be 0, 1, 2, 3. Okay, because we are working in a 4-dimensional space-time. So the indices can be for 3 space, which is coded by 1, 2, 3, and 0th index is basically what decodes time. Okay, so that means mu nu, since we have 4 degrees of freedom, can range from 0, 1, 2, 3. And if I write I and j as you've seen before in the spatial part, this decodes for the spatial indices, which is ranging from 1 to 3. Okay. So whenever I write I, you will understand this is 3-dimensional, which means it only ranges from 1 to 3. If I write mu or nu, which are Greek letters, you will understand that they range from 0, 1, 2, 3. Okay. So now I have this and I plug it in over there. And what I will finally have is an equation that looks like the following. Now, this is the continuity equation of the universe. Okay, so generically, when we're working in flat space, typical continuity equation আমরা কি বুঝি is just the conservation of energy, right? But as I said before, in general relativity, conservation of energy does not really take place the way we think it does. Energy is not conserved in the universe, and that is solely because of expansion of space. And also the acceleration of space, because now the space is accelerating. So expansion in the universe, we don't have energy to be the same. In fact, one of the implications of that is called redshift. You've all heard about redshift, right? So it's a Doppler effect that happens because of the universe is expanding. So what redshift essentially means is that if there is light emitted from a distant object and you receive it here on Earth, that particular light, as it travels through an expanding space, will get redshifted, meaning stretch, and what signal you will receive will have a longer wavelength. Okay, so when does a wave become longer in its wavelength? So let's say I have a wave like this, and I have a wave like this. Okay, so let's say if this has, we can kind of, assume that they are the same wave, and if this has some wavelength, let's say A, the wavelength here would be much larger, right? But just by looking at it, so B should be greater than A, right? When does that happen? When does a particular wave, which is the same wave, increase in wavelength? When it loses energy, right? So redshift happens. This is an established fact. When a distant object transmits a signal, it loses energy when it comes to us. What happens to that energy? Energy is not conserved, right? So that energy is transmitted through redshift, and in fact, now we see that in an expanding space, energy is lost, and therefore energy is not conserved in the way we think energy is conserved in flat space. However, what is conserved in cosmology is this particular continuity equation, which is the covariant derivative of the energy momentum tensor. So this now asserts your energy momentum conservation in the universe. Now, by all of that, we can parameterize this continuity equation. I can write the continuity equation with the help of something I call an equation of state, where the equation of state, omega, is denoted by P by rho C squared, essentially giving you a ratio of P and rho. Now, perhaps I didn't mention this when I was defining what the energy momentum tensor is, but for a perfect fluid, this P is called the pressure of that particular fluid, and as I mentioned, this is the energy density. So the continuity equation essentially conserves both of these components. So now I can solve this differential equation, and I will see that rho is proportional to A to the power of -3 times 1 plus omega. And I can use this now to implicitly define my energy density for different phases of the universe. Remember, A does not scale the same way in different phases of the universe, right? So therefore, the energy density should also be scaled differently in different components of the universe. And of course, এখানে আমি দেখতেছি যে this equation of state is a ratio of pressure and energy density, right? And I know different particles can have different pressure specifications. So that means depending on the components of the universe or what the universe is dominated by, this rho should scale differently, right? So now let's specify that. So when we are doing radiation, or basically when we are in the radiation era, rho will scale as A to the power of -3, and that is solely because rho abides by relativistic properties, right? Because radiation means light, relativistic particles. So in that case, I should have pressure specifications for relativistic particles, and relativistic particles basically have a pressure that is much, much lower than rho C squared, which tells me that I should set omega to 0. Okay, because you can see from here. Okay. So in that case, if I set omega to 0 over here, this basically gives you this result. Now, similarly for matter, when I'm dealing with non-relativistic particles, and for non-relativistic particles, the equations of state becomes 1 by 3 because pressure specification for matter particularly is given by this particular relationship. So this sets omega to be 1 by 3, and I plug this in over there, and I will see that the energy density scales as A to the power of -1, -4. Okay. Now, why is this different from this? Where does this extra 1 by A factor come from? Remember, energy density is what? So if I want to, put it in layman's terms, energy density is some energy by volume term, right? So this is essentially energy by volume, which is proportional to A to the power of -4. Now, for this term over here, I can see that this energy by volume term is proportional to 1 by A cubed, which makes sense because volume is a sort of cubed distance, right? So if I have the expansion of space happening, the energy density should decrease by that expansion of space, which is expanding the volume. So it makes sense for relative for okay, maybe I made a mistake. Sorry. So this should be the other way around. Just when I was talking about it, I figured out a mistake. Yes. Sorry. So this was a big mistake on my part. Let me explain this again. So when I'm dealing with matter, it makes sense for the matter particles to expand with space, right? If the volume expands by some distance cubed, it makes sense for the energy density to move along with the expansion. So therefore, they should decrease by this A cubed term, right? However, রেডিয়েশনের ক্ষেত্রে একটা জিনিস আমি নোট করছিলাম, সেটা হচ্ছে we have redshift, right? When we have light transmitted, it essentially redshifts. So redshift এর ফ্যাক্টরটাও কিন্তু মানে makes radiation lose energy by another factor, right? Which is a factor of the expansion itself. So that means not only does radiation lose energy with the expansion of space, it also loses energy as it's transmitting from one point to the other. So there's another factor of 1 by over here, and therefore it scales by A to the power of -4 because energy in that sense will decrease by an extra term, which is 1 by 8. So that's why I have different scalings of the energy density over here. Now, arekta point jeta I should make over here is dark energy. Right? What is this? Now, remember I told you that now at present the universe is accelerating. So acceleration means something else is pushing the expansion of space, right? So তার মানে হচ্ছে আগে যখন expansion হইতো fine, we had expansion because we had some initial conditions in the beginning of the universe which led to the expansion that we had, right? But now that expansion all of a sudden is being pushed, that expansion rate is increasing. তার মানে you have to account for that increase in expansion by something, right? Something has to push the universe to accelerate. And that particular something is something that we call dark energy. And this dark energy now, as we've seen observationally, has negative pressure. That means that P will be equal to -rho c squared. And if we devise it to the energy evolution, and we will see that it is proportional to A naught, which means the energy density is constant, right? So if the energy density is constant, and the universe is still accelerating, that means there is a higher form of energy that's accelerating the universe, which is something we call dark energy. Okay, and this dark energy is solely the reason why cosmologists are losing their sleep now. Okay, how much time do I have? 13. 13 or 13? Okay. So now, I've defined components of the universe. I've defined how they evolve, the energy density evolves with the scale factor. এখন আমাদের complete একটা pictureের জন্য I need to like not only have possibilities of geometry, like আমি যেটা define করছি যে possibilities of geometry আমি consider করছি, right? Flat, curved, positive curvature, negative curvature, and so on. But I need to define it, right? And by defining the curvature, I need to work out the other hand side of the Einstein's field equation, which is G mu nu. So I need to work on space-time curvature by computing the components of G mu nu, which is given by okay. So perhaps I'm not going to show the derivation, but I can figure out the components where I will have, as I said, mu and mu range from 0, 1, 2, 3. So I can have terms like R00, right? Computing mu and mu to be 0. I can have, let's say, Rij, where I take I and j, which is the spatial indices. Remember, I and j run from 1 to 3. I can have combinations of them, let's say j and something like this. So I can have many terms of the Ricci tensor, right? But as we will see, and because of the symmetries of the FLRW metric, only 2 surviving terms will be there, which is R00 and Rij. And we will see that Rij is in fact proportional to Gij, which is again proportional to delta Ij, because we have a diagonal metric. Because my metric is symmetric, and therefore I can only have it when I and j is equal. So therefore, these 2 terms survive when I'm computing the Ricci tensor, and this equals to and Rij equals to so the way you would compute it is just take the metric, incorporate it in the definition of the Ricci tensor, which I have shown yesterday, I think, and you can just compute it. And it's going to take some time and effort, but you can compute it. So now I have these 2, and what I have to do is now compute G mu nu, right? So G mu nu journal, I need the Ricci tensor and the Ricci scalar from here. So Ricci scalar is just taking the trace of the Ricci tensor. So if I have the Ricci tensor done, I can compute the Ricci scalar, and the Ricci scalar becomes the following. And this is given by just incorporating the components of the metric over here and over here. And this equals to okay. So now I have the Ricci tensor done. I have the Ricci scalar done. What I need to do next is just incorporate them to the Einstein tensor, which is G mu nu. And again, I'm not showing the explicit calculation. It takes a lot of effort and time, but I would really suggest you, if this is your first time, break them down. It will be much easier for you to understand, in fact, learn manipulation of tensors in this way. So in that case, I will have G mu nu. Let me write G mu nu first, which is basically contracted with the metric. And the surviving terms, of course, will be G00, which is given by -3 by c squared, a dot by a squared, ac squared, a squared, r naught squared. And Gij, which is given by the following expression. And this also should be proportional to delta Ij, ensuring symmetry of the metric. Okay, so now I have all components of the Einstein tensor that I need to incorporate into my field equations, right? So এখন হচ্ছে আমি field equations এর সব ingredients পেয়ে গেছি. I know T mu এর component মাত্র বের করলাম. I know G mu এর component মাত্র বের করলাম. I just have to put them together and they should give me my Einstein's field equation, which is given by. So I have all the ingredients to now compute this equation. And once I do that, by incorporating the zeroth order, which is G00 over here, and incorporating T00 over here, I will get an equation that looks like. Does anyone know what this equation is? Except people who did cosmology with me. Does anybody know who or what this equation is? This is called the first Friedmann equation. And this is basically the Einstein's equation for the universe that we are living in. And this is particularly very important because you remember how important Einstein's equations are? We just devised it for our particular universe that has the symmetries of the universe that we can see. So therefore, this is very important. This tells you how matter relates with the curvature of the universe. Matter in the sense, when I say matter, I mean things, constituents of the universe relate to the curvature of the universe. And of course, I'm not done, right? Because I only incorporated only incorporated the zeroth order terms here. So I also need to incorporate the i's and j's, these terms, right? So I have Tij and also Gij, which if I plug it in, which means if I incorporate this equation, what I will get is the following expression. Now, this not only is called the second Friedmann equations, but this is also called the Rai-Choudhury equation. Now, you can also incorporate this by taking the Ij components of the Einstein tensor and the energy momentum tensor, but you can also find it by taking a temporal derivative of the first Friedmann equation. And it is easy to show that both of these equations are very fundamental to understand the dynamics of our universe. Okay, so this is where I will stop today. And if you guys have any questions, you can ask.
For everyone, we'll do the main school registration during lunch. First 30 minutes will be people outside BRAC University, not affiliated with BRAC University. And yeah, so the next 30 minutes will be BRAC students. So yeah, that's how we will do the payment. And so our last session will start at 3:30, so that everyone has enough time for lunch registration. chilling. So we saw 10 minutes. So frequent equations are super nice because it's very simple and you can describe the dynamics of various phases of the universe using the Friedman equation. So for me, it really looks super nice, super cool that the matter phase, radiation phase, this phase of the universe, it's super nice.
One thing I want to add, maybe I didn't mention, is that rho and p was independent of my phase, right? So that means the Friedman equation actually worked for the entire universe. So throughout the history of the universe, you can in fact also denote the Friedman equation for the element that we are in today, just by explicitly specifying rho and p, which makes the Friedman equations very generalized and very beautiful.
Start with 5 to 10 minutes. Again, one of our volunteers, it's his birthday, Riyad Shafqat. So he reminded me, happy birthday. So he repeatedly reminded me to ask everyone to ask him questions. So please ask him questions. He's on Discord as well. And he says, for every question, one shingan. Yeah. So he gives the shingan, of course. So one question to Discord, he gives the shingan. So feel free to ask the shortcut questions. No, you deal with it. You make sure.
মানে এটা কি ক্যামেরা ইমেল সারা রাত ধরে আমরা ঠিক করছি প্রথমে এটা বানাতে গেছিলাম তারপরে দেখি পরে হলো